Okay, so let's get going. Glad to see everyone again. So the plan for today is the following. So we'll quickly discuss like what is that we plan on building, like what kind of operating system we want to build over the period of this semester. And there is like, it's not like a huge discussion, but let's just talk through it so we all understand what is going to happen. And then I'll start talking about how to boot into Rust, essentially, how to like get into like how to get Rust running on bare metal and like implement print function, essentially, just set up the page table, stuff like that. And the idea is that I'll try to assign the homework as soon as possible, but I don't know when it's possible because you guys should say, look, we're ready to handle at least some minimal Rust. It's really minimal at this level. Like probably it's a day of studying Rust to use the Rust which I will use here today. So it's not hard at all. But so maybe like beginning of next week, even just get going, and then we can discuss how to assign the homeworks to make it the most productive thing. Okay, so let's start with planning. So okay, let's start to discuss what is that we really want to build when we. I mean, let me to provide a concrete example. So not too long ago, we were working on this new operating system, which is called Atmosphere. Since it was fully formally verified, or like we wanted to construct this mathematical proof, any extra feature is additional burden. Like you build something, you have to build a proof about it. And we don't even know whether the proof is possible or feasible within like manageable time. So we wanted to build the smallest possible operating system. But on the other hand, it has to be a little bit of use. It has to be useful because we need to run some benchmarks to submit a paper. So it has to run some user land. Maybe it's like some device drivers. We don't have a file system, but we have like something like a web server and some other like tiny applications. So imagine that's the setup, the minimal operating system, but it has to be able to do something useful, like I don't know, print on the screen, send network packets, allow building applications. So how can we build one? Any ideas? What will we build? Abstraction for a process, right? So, oh, Jesus, that's too fast. No, that's the final slide. Not right now. Sorry. So again, so I keep teaching you in an undergrad version of this class. I say, look, the end goal for us is to run some user land, right? So this is a process of P1, let's say, right? When you say abstraction of a process, what do you mean by that? What is that we need to build? Like roughly speaking, to be more concrete, let's say it has a main. Usually I have better handwriting. Okay, probably it's not my lost ability to write on this thing. Yeah, but this is main. So we have to be able to enter main and start executing code inside main, right? What's the minimal sequence of things we need to build, or minimal set of things we need to build to get to this?
You need RC.
Okay, that's an interesting idea. So you say, look, we want to parse arguments. You specifically said, okay, I wanna follow a specific argument convention, which is popular Unix, right? Like again, that's imagine you have to build a proof about this. You quickly drop this requirement and say, no, my functions will be all void. Because to pass arguments, really, you start plotting arguments, and it's a good design choice, but only when you have a shell, then you have general programs, and I'm with you. So let's get to arguments, but maybe not right away. Again, maybe void is good enough for now, and we'll come back to it, and maybe when the shell's idea of an argument, the way shell passes the argument, and the reason is probably historical, is that because everything was controlled from a shell, and then different utilities were implemented as programs, and the RGB convention was geared towards passing strings. So you can say, look, do something with this set of strings, and then and that was useful. It's kind of like we today control Amazon data center. And if you ask me how we control it, I don't know because I don't, but you probably know. But we like run a bunch of machines, pass arguments, stuff like that. So I guess JSON1 or something. But so arguments are there. And you mentioned the second thing, which is interrupts. And it's fine. But again, we will get back to it. I agree that we might need interrupts, but maybe not. Let's discuss it because it requires building. And I mean, in this class, I actually do want to build interrupts, but let's not immediately jump into it.
So at the very least, I would say for a process abstractly, you have an execution. So at the very least, the program should be able to send its instructions to the processor to execute.
Well, hold on. Like, that's very abstract.
Okay.
It's almost like I'm reading a book. But really, like, we know that if we have a good compiler, like we took some kind of a source file right here, some LLVM compiler, and it produced us an executable, and we're clever enough. It's already machine executable code. Our end goal is to, at some point, get instruction pointer set to main and start running. If we want to pass arguments, we'll set up maybe stack, push arguments on the stack. But let's be concrete. I don't want to be abstract.
We need a scheduler for multiprocessing.
That's also a good idea, and I will put it next to arguments and everything, and I agree with that. So we want to do a scheduling if we want to support multiple processes, and it's totally fine. I'm with you. And then interrupts kind of plug into the scheduling because you say, look, really, if I'm completely super lazy, the only interrupt which I need is a timer interrupt so I can triggers a switch from one process to another. Right, that's good.
Something to boot into.
Okay, sure. Yeah, I agree with that too. So we need a bootloader. But and that's a sound idea, but essentially at some point we say, look, we like imagine there will be a layer of a kernel here between the process and the hardware, and at some point we need to initialize the platform. If we like, again, historically this part is called the kernel, right? Which that's what we're building, right? And we need to, again, get to some kind of a entry point of the kernel. And we say, look, before even getting to that entry point, we need to initialize the hardware. And some part of this hardware initialization is kind of orthogonal to what the kernel will be doing. For example, you say you got a motherboard, right? It has a CPU and a bunch of DRAM banks. And hooray, like even before we start running the kernel, there is a ton of stuff which is executing. Like the memories have to be like all these memory channels and the frequencies of those, how many millions of transactions per second you can do on a memory have to be initialized. Everything has to be queried. How to do it, I have no idea. And very few people in the world know, but you would just say, look, I trust Intel and whoever, like whatever they like, and their partners, and they say, look, run this piece of, it's called firmware, but really it's just some code which executes before you and sets up the system to the state in which you can access memory, right? And I do teach occasion, I do discuss it in my undergraduate class. Honestly, I have no idea how it works. Like it's a black box. You just say like initialize and it initializes, and they're like really like a handful of people in the world who knows what's going on. And this part of initialization or booting is not so interesting to us because unless we're security researchers who know that we can find a bug in this initialization protocol and then exploit it, maybe like take over the system, we don't really care. We just say, okay, look, we want memory to be there, registers in clean state, give us the instruction pointer at some specific address, which we provide entry point of the kernel, like this entry, and we will start running from there, right? So and there's some microcode, like, you know, Intel ships you microcode updates, like CPU has they have bugs, and like Intel says, hey, we're gonna fix some of them in software, something, right? There's a lot of stuff going on, right? But and we can discuss, but I don't know if we can come back to it probably. There's a ton of stuff running, right? But we want to, at some point, our ideal goal is to get control from the bootloader. The reason I started talking when you mentioned bootloader, idea was that we will discuss it a little, but ideally, if I'm very lazy person or like I'm on a short deadline, I'm not going to build a bootloader because it's a lot of pain, and to get it right is also hard. And so ideally, I would like to get an existing one, right? And let's say we all seen it, maybe not everyone, but Grub is a good enough bootloader. It's built by Free Software Foundation. It's open source. If you looked at the source code, your hair will go up. Mine went. Like, sure, like I didn't look a lot, but I appreciate the effort. It's not easy to build those things. So, but it's there. So let's assume bootloader. Someone gives us a bootloader. We will talk a little bit about the protocol, how bootloader knows what it's working with. But let's assume we can start working with the kernel, right? Meaning this piece of code which gets control after the bootloader, and somehow it works. So, and I agree with all these things, like we should mention. We're going to build supposedly a timer interrupt scaler. The original idea was to get to this, to be able to run user processes, right? And what else is missing to get it run? We need system calls, and system calls are the way to invoke functions of the kernel from user level. So we need some syscalls, right? And the reason, there are multiple ways to think about it, right? So, but the most typical way is to say, look, by the way, in the end, we don't really trust user code. It's not always true. Like there will be operating systems which you see in your life where the user code and the kernel, they're just merged together, run in a single address space. Someone was bringing up concept of unikernels last time. That's one way. So the kernel is a library within the process address space. But typically, especially if you want to support processes from multiple untrusted users, right? You would like to have some kind of isolation between the kernel and between each process, right? And in order to invoke the kernel, you need a layer of syscall, which is like a trusted entry back into the kernel, right? I agree with that. So that's good. Like, and if you imagine, to make it concrete, our very first user process will be just printing hello world on the screen, right? So that's the best we can do. It's like in a language, if you want to learn something, let's print hello world. And arguably this syscall will be specifically something like print. Or if we want to abstract it, in x86, it was a write into whatever standard script, right? But that's the same idea. So that's sound. Yeah, we need to get some output from the user. Yes.
So not so much an idea, more I'm thinking about challenging. Like here, we're still assuming
Yeah.
And we've also spoken about the kernel not being entirely trustworthy.
Mm-hmm.
Just like this. So in a hypothetical world, in can we still challenge the requirement of the user level? Could we have could we have a bare bones operating system and it's all processes run as code?
Yeah, so that's this idea of unikernels. That's what they do. That's the idea where, the idea is to place the kernel as a custom library inside the link together with the whatever, some user code. It can be a database or Apache web server or something. And put it inside some kind of a container. This container can be a virtual machine, or and virtual machine can be different. It can be hardware virtualization, or can be just a process on a container-based operating system, right? And the reason you do this is that, like, there are multiple reasons, but maybe you have some funky dependencies, and the kernel which you run here, which might be a hypervisor, or just some other execution environment. So this kernel 0 does not match kernel 1, and your code, like maybe it's some legacy stuff, it's like only works on this kernel 1, and you link. But their original argument for unikernels was performance. So they were fast to start, and they had a small footprint, meaning that you can run hundreds of those on a single server in a cloud, and it was cheaper for you. And so we can come back to this. I thought that we were discussing it in the other class, which I taught last year, but we can come back to unikernels versus something else a little later. That's doable. And another, like the most practical scenario where your kernel and the user will be in a single address space is some embedded system, which is so constrained that it doesn't provide abstraction of address spaces. Like imagine you trying to save every bit of energy. And I keep using this example because there are ways to harvest energy from the environment. Solar panels, but vibration, other stuff, radio frequency waves. And so you say, look, I only have budget of so many watts, right? And I say, my CPU is so simple, it's all in order, and memory subsystem doesn't exist just because, TLBs and page tables will take so much energy that I don't want to keep them. And then you say, look, in this specific embedded environment, you still have a kernel and a user, but it's all kind of bundled together, right? So that's probably realistic. And then what you lose is the ability to isolate processes, right? And if your scenario allows you to say, look, I trust each process on the system is trusted and reliable, then it's okay. If it's not, then the story is different. Okay, so back, but we derailed a little bit. Like, let's get back on the list. So what else? What do we need to build to get to main inside user? Yeah, that's actually quite clever. I managed and I forgot. So you say, look, we actually need to do some kind of memory manager. And that's to essentially, because all this thing will run on top of some kind of limited amount of physical DRAM. And I mean, we will build virtual address spaces on top, but still physical resources we have to manage. So, right. I mean, again, you can go extremes and say, look, everything is statically allocated, and it's a single use case scenario, and I know upfront how memory will be partitioned and managed. But again, in most cases, you need a memory allocator. So that's a good idea. So this will for sure we have to build. You had an idea as well.
I was going to say that.
IO devices, correct. So at least if in our use case we say if it's a hello world, then we at least need to build like logic to print something on the screen. The easiest way is to use VGA. VGA is this like prehistoric format which allows you to like write some ASCII characters in memory, and then the hardware reads them from memory and has enough logic to put real letters on the screen. But that's good enough. It will print hello world, right? That's what we did as a homework assignment in the undergraduate class. And ideally, since we don't always have VGA, right? We're gonna print on serial line as well. Just it's sometimes easier in a data center. Not always VGA is not always available, and that's fine. But that's kind of like to get running and print hello world. But if you want to be serious, like even for my paper submission scenario, I needed to support some useful device drivers, and those useful were like you immediately pick two. What will be the two which you pick to show? Keyboard? Well, it's useful, but not for reviewers because they want to see some performance, something performance sensitive. Network is a good example. So yes, we build a fast network adapter, and GPU. Good luck. If you do GPU, you will be my student. GPUs are hard, and the parts I don't even know the full stack, but they're partially proprietary, and some parts are open. GPUs are hard. We built NVMe. NVMe is a fast disk. In the past, we used to build HCI, which is like a standard, spinning disk protocol. I think it's called HCI, right? I don't even know what it stands for. But these days, the fastest disk is non-volatile memory over PCIe, which is called NVMe, right? And that's like all laptops come with it. And like really, it's kind of, if it runs fast, you can believe that the system is decent, runs fast, right? So yeah, so we can build a network and NVMe, and is there like, okay, maybe not. Let's do NVMe device, right? Yeah, so this is good. So let me think what we missed. So interrupts will help us to support scheduling. We need scheduling. We need system calls to enter the kernel to print something and maybe communicate with device drivers. We need some memory management to allocate physical resources. One other thing is missing. It's a little hard to guess. We need some kind of an idea of how to load this process in memory. Okay, hold on. So one thing which I would expected you to say, we need abstraction of address spaces, right? So because you say memory management, but memory management is kind of like, if we imagine seats in this room, this physical memory, I keep just track which seat is available, which is taken, right? And that's my allocation algorithm. I just look at my list and say, look, this is free. But that's just allocation. If we want to isolate processes, we need address spaces, meaning that I just suddenly like roll a wall across the room and say that half of you don't see the other people, right? And we know what address spaces are, but we need to build them. So it's basically building a page table on most hardware, right? So page tables as address spaces. So because the process itself is roughly speaking an address space, right, from x86, syscalls allow to transition back into the kernel, right? So, and the other thing which is missing is some abstraction of an ELF loader. So like if we have at some point an NVMe device, maybe we'll have a file system, maybe not. Maybe it's a simple in-memory file system, maybe something else. But at some point when we probably want to implement a system call which says start a new process, something along those lines, and this start a new process will pass some kind of a pass or an idea of an binary image which we want to start running. And typically a little bit of linking and loading is required. Although x86, for example, doesn't do anything. So it just statically linked. So maybe we can get away without it. So kind of ELF loading. But it's honestly not hard to write or develop. So maybe ELF loading, we'll build some minimal one, right? Okay, so this makes sense to some degree. Let me just kind of like reiterate it, but backwards. Backwards meaning that to kind of just reusing this slide. So we say, let's start with building the kernel binary, right? So it's a kernel, it has an entry point, kind of like a main function. We need to make it, we need to be clever enough. So we need to maybe add a specific header to this binary and to make sure that the bootloader will be okay loading us on the physical memory of the hardware, right? Then in order to get to the process, and it's very similar to how x86 does it, you will set up a page table, right? Because you say, look, maybe, first of all, maybe the kernel itself needs a page table because it has to run in the protected mode, right? So we will immediately initialize some kind of a page table. So outline as a build a page table. In order to build a page table, what is that we need before the page table? Remember, quickly think about x86. What's the very first function in x86 inside me? Segmentation. Segmentation was before main and after, much later, but you're close. Well, page tables are hierarchical, right? So
Free range.
free range, okay, good memory. So what is that free range about?
I think it just kind of frees all the memory after.
Yeah, after like all available mapped physical memory. But what I'm getting to is the page tables are don't forget that they have layers, right? So the page table has a root, then it might have multiple levels. And in our case, since we're working with 64-bit mode, the minimal amount of okay, not the minimal, but let's say normal amount is 4, right? So even if we want to add like one mapping from virtual to physical, underneath we might need to allocate those nodes, right? The pages which contain the page table. For that, we need memory allocator, just because if we don't have a memory allocator, we don't know where to get this memory from, right? So, and this is what free range was doing. It was initializing the memory allocator with some minimal amount of pages. And like realistically, we need init memory allocator. Then build like to the page table, then roughly speaking, our elf, if we decide to do everything statically, then no elf, but just simply loading or constructing of the process. Remember, it was exec function or fork function in x86, no exec, obviously, right? So essentially, if you know how to build the page tables, you can build this outer boundary for a process, right? So that's just a page table. And in order to load something meaningful like the main here, which will be running, you need this elf loading, right? In order for the process to get back to the kernel, right, you need to build a syscall interface, right? Because whatever it says print or something. And in order to even like at this point, you kind of roughly saying, okay, I can exit into the process, but you have a dilemma here. You may not get control back ever, right? Because if you don't set up the timer interrupt, the process might immediately start running an infinite loop. You will never get the CPU back. So ideally, you should kind of like set up timer interrupts, timer and other interrupts to make sure that the moment the specific like amount of time passes, you get a timer interrupt and you get preempted, similar to how x86 does it, and then you get control. And at this point, someone said, okay, we really need a scheduler, but for real, maybe we don't, right? And we will like, roughly speaking, if you're running one process, you will be just bouncing back and forth between the kernel and the process, but let's build a couple, right? And for that, we will have some kind of a scheduler. Like we can do something similar to x86, or we can build something a little smarter, but not too smart. And then just essentially at this point, we can like support multiple processes and they can run and we can switch between them, right? And that's good enough. That's almost like x86. Besides that, the only thing it can do is print, right? Because we didn't build any IO devices, right? And if I say, look, I want to build a network device driver. So device drivers means it exposes a high-level interface, kind of like a send and receive a packet, but internally handles all the complexities of like actually sending the packet. So like triggering the DMA transaction, whatever, and like talking to the hardware, setting up the hardware, right? xv6 said, okay, first of all, in xv6, we didn't see much device drivers, but it had this IDE device driver, which is like even simpler than AHCI or NVMe, but they put the device drivers inside the kernel, right? So it was sitting here in a kernel. And it's one design choice. That's how most operating systems like Linux, to some degree, Windows and Mac OS are doing it. But the tendency today, like you say, in 2025, the tendency is to move out device driver and run them as regular user processes. Why do you think it's the tendency?
The API exposes prevents misuse, maybe, so it doesn't need to be in protected space. That's my guess.
Let's take another answer, maybe.
There's a lot of.
Correct. Remember, like my intro lecture, I mean, despite the fact that it's showing the fun pictures and everything, the map of the Linux kernel, even back then, was roughly 8,900 device drivers. I don't know the number today, but it's definitely above 10,000. And device driver, every time someone builds a new piece of hardware, says like, I want to run Linux on this new piece of hardware, they add code to the kernel. This code is written by people like us, sometimes even less indicated, a lot of amateurs. But that's one part of the problem that a lot of people don't have background knowledge. The real part is that the kernel is so complex that even the most proficient kernel developers cannot get it right. It's just no one has a complete understanding of this kernel interface and all the possible invariants which you have to maintain in order to get this code correctly, right? So bugs are introduced into the kernel, and if you push them outside, then if there is a bug here in this device driver, that's the bug, then the user process crashes, and maybe your system at this point halts, because if it's a disk interface and you had some packets in flight, meaning like some IO requests in flight, it's almost impossible to recover. Roughly speaking, it's sometimes possible, but it's hard. If it's a GPU driver, then maybe you can just simply restart it and then you will get your screen back, because nothing really like, or if it's a network driver, who cares? Like if we lost some packets, right? If it's a disk, it's harder. So some device drivers are critical, some less, but at least, you know, maybe it halts, but at least the attackers do not immediately own the entire kernel. They only own this tiny little process. Their authority is minimized. So that's a kind of like a security measure. And so if I understand correctly, and I didn't look recently, but macOS pushes very, very hard for pushing device drivers outside of the kernel, to the point that I don't think they even allow anymore. But they used to, but now I think it's all runs as user level. I can be wrong, but we can talk about it more. Windows, it has layers, but I think it still sits in the same address space. Linux has only minimal support for user level device drivers, but at least it does exist. And like prominent examples are Fuse file system, user level file system, and maybe some other DPDK, SPDK are good frameworks, right? So that's one reason is security. What's the other reason? Since I mentioned DPDK.
Because you can have without having.
Correct. So it's a little bit counterintuitive, because you say, look, we pushed it outside, so it's further away from the hardware, supposedly, right? But it turns out that modern kernels allow you to, they expose the interface, which allow the user level process to talk to the hardware directly. Maybe there will be some kind of a control plane, which has to go through the kernel. The kernel says, okay, we're gonna validate that what you're trying to do with this device is legit, but then other I operations are what is called data plane. And it's a principle of separation of control plane and data plane. Control plane can be slow, but you set up device only once. Data plane is extremely fast. And conceptual observation for why you get performance is that typically, like if you put the device driver in a kernel, there are layers of protocols surrounding this device. But for example, if it's a network interface, you probably have to go through the kernel stock TCP/IP, yada yada. And in Linux, if you go to the storage stack, there will be layers of scheduling, because like the kernel says, okay, this device driver will be, or this device will be fairly shared across multiple users. There are some sharing policies. What does it mean to be fair? How to enforce like load balancing or whatnot. And you say, look, but by the way, I'm a single user of this device or this machine even. Maybe I run some shells and stuff, but really what I'm running here, I'm running maybe Facebook, and maybe it's like memcached, and really like it's a sole user of this device and sole user of this device driver. And then you can essentially cut all these layers of software which provide these general interfaces, and like implement minimal logic which allows you to talk to the device directly. And it does has a huge boost for networking and disk workloads. So specifically DPDK it stands for Data Plane Development Kit, is the idea that you run network applications against user level network device drivers, which talk to the hardware, and they achieve performance of like middle boxes which you buy custom built or whatnot. Like roughly speaking, it takes less than 100 cycles to process one packet. It's a huge kind of it's 10x performance benefit, right? So sometimes you do push them outside for performance reasons, but main reason is probably still security, because most device drivers are not as like performance hungry, right? So talking like coming to this idea, what I wanted to get back to, let me just maybe erase everything. I suggest that we in this class, like just following kind of modern trends, we're going to build device drivers as user level processes if we get to this, and I hope that we will, right? Which means that like where I was drawing it here, but here is not space, so let's go back here. If we build our kernel, what we're going to be building in the modern literature is called a microkernel. Typically, people put this letter, kernel. And the microkernel itself is very minimal. There are some additional benefits for why you want to build it. It's smaller. Remember, my original goal was I need to verify everything. I build mathematical proofs about that everything what's inside the kernel is correct. So the less stuff I put into this layer, the better. And the same argument holds informally. So even if I don't have a mathematical proof, I say, look, if the amount of privileged code is minimal, there is a smaller chance of finding a bug in this code, right? So the less code goes into the kernel, or if we call it a microkernel, the better. And then our device drivers, they run as user level processes, right? So it's like, I don't know, network interface device drivers. Device driver, it somehow talks to the hardware, and maybe microkernel sets up something, and we talk about what it is, like IOMMU table, stuff like that, maybe interrupt routing. And my processes here, like user stuff, also run as user level processes, right? So then my architecture looks like this. So this below this line is privilege level, or something what we usually call, on Intel, ring 0. And this is kind of user level, or ring 3, if you want to compare with x86, right? Make sense? Let's just quickly reiterate, what does go into this kernel? What is this minimal functionality which goes into the kernel, which we really need to put in there to make everything running? It's pretty much what we said, but let's say it again. No, yeah. So,
Memory allocators, page tables.
so memory agrees, memory allocator, page tables or address spaces, right? What else? Interrupts. And you're right, because we probably will put a scheduler inside. And so at least the timer interrupt will be inside. So timer and scheduler. What? Loader, yeah. I will show you the trick that you can actually push the loader outside. If you temporarily give one of this, like if the parent process has temporary access to the child process in its address space, then you can say, look, if microkernel was not involved, whatever the parent sets up will be running. And if you trust, and the parent can play a protocol with a third-party service, it's kind of like a flushing machine in a data center. You don't have to implement flushing on the machine. You just like network boot, and then it boots. So it's the same idea. So technically speaking, maybe loader can be pushed out, but let's put it here. Yeah, system call interface to make sure, yeah, syscalls. And what else? So in like conventionally, people also say threads, because microkernel like it accounts for what's running in a system. And if we want to support threading, meaning inside one process, multiple threads of execution, then we will say that we will count at the level of threads, and then threads will be connected to a specific address space, right? Then meaning that they share the address space. And one thing which is completely kind of counterintuitive, right? But I wanted to get to it. Okay, that's all nice. You actually enumerated everything very nicely. How do we talk? How does this process get access to the network interface, network device driver? Because they run as individual, two separate devices, two separate processes, sorry. Correct. So I didn't mention it on purpose because it's somewhat wasn't really needed up until now. I mean, maybe I mentioned last on Monday, but it's called IPC, inter-process communication. Like we've seen one mechanism, right, which is a pipe in xv6. And it was kind of like in xv6, you can write on one end of the pipe and read on another end of the pipe, right? That's fine, and it's one flavor of IPC, but like first of all, it's important to understand that IPC goes into the kernel because there must be some way for these guys to like talk to each other, right?
There's also the mail system, send mail. I don't know the correct term.
Not really, but we'll get back to it. Don't worry. Like, yeah. So that's closer. So, and I wanted to discuss a little bit, but roughly speaking, like pipe was fine, but its pipe is almost like a network interface. But really, if this is a network interface device driver, you kind of want to invoke a function. You don't want to write into a pipe, although you can, but you really what your intent is to say, look, receive a packet or send a packet. So it's almost like invoking a function, right? So, and like if you took networking classes, you say, look, I know how to marshal arguments. So I will just marshal everything, whatever JSON or some more efficient marshaling scheme, and just like push it into the pipe, and then it will come back and I will unmarshal, right? And roughly speaking, something similar will be here, but ideally, since we say, look, if we send a lot of packets, this path really has to be fast. So we will take a look at how to try to build this this interface in such a manner that it resembles the invocation of a function. It's just in two different address spaces, but at the same time, it's very, very fast. And sometimes you say, look, but not everything in my life is a function invocation, because sometimes I want more like stream stuff. I really want to send like a ton of packets into this network device driver, and invoking like crossing the boundary and invoking a function every time is just simply too expensive. And at this point, we get back to something what Axel mentioned. It's more like you say, look, what if we can share a region of memory between these two, and really just implement some kind of a queue in that shared region? Then, you know, one, like a process can keep adding to the queue. And if the device driver is running on a separate core, it can actually in parallel keep fetching from this queue, and everything is super duper fast. If we are unlucky and there's just one core, then we will be context switching like on a timer interrupt or yielding, right? It's more like a pipe, but what I'm saying is it will be like more a glorified fast pipe. And it's mostly used for if like essentially there are two use cases: synchronous invocations of functions, meaning that you're waiting for the result of a function, and asynchronous, let's pipe as much as we can. And we need to optimize for both. And the interfaces will be slightly different.
Isn't that
IOU-Ring is an interface between the user level processes and the kernel in the Linux kernel, which replaces the system call interface. Because instead of going horizontally, which is actually much slower compared to go vertically down into the kernel, because the CPU optimizes this path. So syscall is like 100 cycles. Going horizontal is 800 cycles on one port if you do a context switch. On Linux is like 5,000 cycles because they don't optimize for this. But yeah, IOU-Ring is one implementation of this buffer.
This shared memory, do all processes access the same shared memory to send to it? So it's like a queue that can receive from multiple different processes.
It's implementation specific, and you can set up different scenarios, and it's all like trust and whatever is going on. You're right that if there is a network device driver, obviously will have multiple clients. Most likely we'll set up a private queue. Each client will have an individual queue, because then they cannot screw each other. It's easier to blame, but maybe there might be a scenario where you want a shared queue. Most likely not. I haven't seen it recently, but maybe it exists.
So this fast IPC path that you mentioned, synchronous operation, is that motivating sharing that?
Hold on. We'll explain why the shared libraries and shared objects are.
Like, I guess I'm just, I don't even know if shared that means. You have the other library runs its own space. It is exposing function calls.
Oh, yeah. What do you, I mean, like, maybe last time we talked a little bit about, I asked, what is the real example of isolation in the modern world? And you said web browsers and web browser plugins. You can also mention something like WebAssembly, which allows you to like safe execution of unsafe C or something code, right? And you say, look, that's my, really, I don't trust the third-party library because I got it from whatever, some website. It was updated 3 years ago last time. Just like says about, and then you say, look, I want to run it in a separate address space. Yes. So that's a use case. And then it's typically a synchronous interface because you really invoke functions. And then yes, that's the use case on modern hardware in modern world. It's called, I think the word is compartmentalization of, like you say, one process, but internally it's cut into different partitions and each of them is isolated. It's possible on modern hardware with different degrees of performance loss and stuff like that. And WebAssembly is a popular way of doing it because, like, on some workloads, you lose 10% of performance just because you enforce this memory checks. It's software fault isolation. And on some you lose 40, but when you lose 10, it depends on how frequently you're crossing the boundary. In WebAssembly, the function invocations are very, very fast because you don't change the address space, no changes in hardware. There are different, like these days, hardware vendors are trying to come up with better fine-grained address spaces. Everyone does, like all the vendors. And there are some like amazing projects like hardware capabilities, which is called Cherry or Morello, stuff like that. And there are less exciting, but deployed in real hardware. So ARM, which we're running here, has memory tagging extensions and has also PAC, so support for pointer authentication, and you can build those isolation schemes on this. Intel has memory protection keys. So it's like within one address space, you have like 15 different address spaces. Okay, so IPC is a little counterintuitive, and we never seen it in x86, but we're going to build it here because everything will be a microkernel. And in order for the process to communicate with anything else, even for the network interface, invoke a function, we have to build something. So tell me, like, give me a hint. The answer is obviously yes, but I don't know where you're trying to get.
I'm just saying, like, what would be like different concepts for a facility within shared memory?
Okay, hold on. We can talk for a sec. Let me just scroll to an empty slide. So, and probably APC should be like a separate, maybe a lecture or two, and we will get to it because it's coming your way. The reason, I mean, you can hide from it, but the reality is that the software is exploitable. We have a ton of legacy stuff, and sometimes, like a huge tower of sensitive software falls because there's some library logging, like anecdotally, some logging library from a third-party site at the bug, right? So we will try to compartmentalize software. And conceptually, if you think of it, it's in many cases, it's execution of a function. So it's maybe takes a couple of arguments, int A and int B, right? And what you're saying is that, can I just invoke this function, but in a different address space? And if you have some magical instruction, exchange or something, adder, which changes the address space, then roughly speaking, you may push these arguments on the stack, but maybe stack becomes invisible because you probably don't want to share the stack. So maybe there will be some kind of a small region of shared memory, and you're gonna push the arguments here, or maybe you can leave them in registers even. And if that's what you mean to facilitate the IPC, that's one way to marshal the argument. So essentially, the question here is, how do you marshal? If on the other hand, you say, look, I'm sending a ton of packets, it's not like invoking a function, then it makes sense to build, like, allocate a large region of shared memory. And it gets funky because you say, look, maybe there are objects of different sizes. If it's like, then you have to keep track of which memory is free, which is not. And so people worked on it and figured out different approaches for how to efficiently send stuff across. And typically it means that there will be two regions. One contains the ring, and then the ring will contain pointers to actual payload if payload is different size. So those are the tricks. And also, if you're absolutely crazy, and we're currently actually working on something like this, we do this work. We say, look, like we did take a look at all existing hardware mechanisms, and we said, okay, look, guys, Intel, ARM, and even Cherry, and you guys, you're not good enough. It's still slower than the function. And then we want to build new hardware or hardware support for how to do it fast. And we're trying to push it to the extreme. So far, everything is rejected, but eventually I think we'll get in, right? And then the idea is to make, like, we know the overheads, and it's roughly, it's like at least 50 cycles, and it's kind of a lot because a function invocation is like 5 cycles. So hardware support is kind of necessary to make it fast, and then the world will change. It will change sooner or later for you as well. So you will see it if you stay in this field. Things will be compartmentalized eventually, but like in a couple, maybe in 5 years or something. So it's coming. But yeah, so like keep an eye on IPC mechanisms. Person, good. Okay, so but back to this. Okay, so this is a good enough of an outline. It's even like maybe even more involved than I wanted, right? But like we kept track. We kind of like design everything together. So at this point, that's the plan. So we will start step by step. Our first step, like our final picture, will look something like this. It's probably a picture from our paper, just writing my kernel. Doesn't matter, but essentially like multiple processes. You have IPC threads running inside each process. There is a send primitive which allows you to send messages to an endpoint. An endpoint can is inside the microkernel itself, and other process can have been received from the endpoint. So essentially, that's what we're going to build, and roughly speaking, that's the classical idea of micro, right? And it's good enough. So, like to be honest, as I was saying last time, if someone were to build a new system from scratch today, they would probably start building a microkernel. One anecdotal example is this Google. What's the word? Fuchsia. What's the color? Fuchsia. I think the micro fuchsia. Yeah. So that's the name, or magenta. I forget which is user level, which is microkernel. But that's the microkernel which they are piloting as an alternative to Linux kernel on Android devices. I would say they made a couple of unsuccessful design choices, but with unlimited resources, they will be successful. But essentially, that's a good design. So like push everything outside of the kernel, and my Windows NT started in the same idea when I was a kid. So maybe you missed the time frame, but essentially before Windows NT, there was Windows, which was running in a single address space. Windows 85 or 95, Windows 98, and then NT was a new kernel. NT stands for next what? I don't know what next. I don't know what is. Yeah, but and so they designed and built it as a micro. So there was a small nucleus, and you will like occasionally you read documentation and you see that there is a name, something like kernel DLL or something like that. That's the core kernel, and everything else is conceptually like is a different process, but they ran into a problem. Switching isolation boundaries was so expensive for them, they had to give up, and they run everything in a single error space. Privilege level 0. This, I mean, I don't follow Windows development very closely, but almost like as of like 5 years ago, for sure we're running everything. Now they put something out. But inherently, it's kind of like a microkernel in which they erase the isolation boundaries for performance reasons, because they could not keep up with non-isolated kernel. But what's more important is macOS. macOS is really a microkernel. So it somehow they managed to, maybe they started a little later, or I don't know the history, but really they took a different microkernel, which was called Mac, which was, I think, developed where either UBC or I forget the name, but essentially, and they took device drivers from FreeBSD And they're like different setups, but essentially it's kind of a mix of a microkernel plus monolithic kernel. Like when you run everything together, it's called monolithic because it's. But really, the systems which are running are kind of like a mixes of both. And Android, it uses a monolithic Linux kernel, but then they push so much operating system functionality, like so much operating system critical functionality into user processes that it's almost like a microphone. It runs as user processes, all this GUI stuff and stuff, right? Makes sense? Okay, so that's what we're gonna build. So that's good, makes sense. Any questions for now? It sounds like a plan. So it's not super goofy. It's better than x86. x86, by the way, is monolithic because device drivers are running inside the kernel. Also, x86 exposes the canonical Unix system call interface, and our microkernel, I forgot to mention, by the way, will be exposing just send and receive primitives and a handful of maybe system calls which allow us to create a new thread, maybe create a new process, which means create a new address space. Because there is nothing else. You don't need to like write file. Right? The file is not in microphone. So you really have to send a message to the file system service, which we'll implement as user level. And I'm not saying that we get to file system, but at least conceptually, right? Makes sense. So the only interface is send, receive roughly, plus system calls to create threads, allocate memory, like everything what we wanted to put in the kernel. So like I said here, like create an address space, allocate probably physical memory, maybe manipulate your own address space, map the memory somewhere. I don't think you need, like maybe register a thread to listen on an interrupt, and we'll talk about it. Set priorities of the scheduler to say, look, some processes are more important, like minimal syscalls, just essential interface to create threads. But everything else is send and receive as a system call, as an IPC mechanism, right? Okay, cool. So that's good. And took me a little longer than expected, but still we probably can start. So our first step, and that's not surprising, and we did it as homework. So we booted into C in undergraduate class, right? So remember, we set up all the segmentation and paging, and then we did hello world from C. What we're gonna do, we boot into Rust, right? Because we want to work in Rust. By the way, I sent an announcement on Canvas saying, okay, start working on Rust. Because like we will see some Rust today. Okay, so okay. What do you think? What's involved into booting into Rust?
Well, first of all, there's probably no access to standard library, right?
Yeah, that's very clever. No standard library. Yeah. What else? And so, what does it mean if there is no standard library?
No, like it.
No malloc. Yeah. Yeah, no malloc. What else? Actually, it's kind of trickier. You can actually corner. So I don't know the answer, but because you allocate on a heap, right? Rust has an explicit primitive which involves. So you can, yeah, obviously it will not be implemented, but yeah, so no, yeah, everything will be allocated statically or on the stack. And if you want to do box, you will have to build support for it. And I will show how, and then box will internally call an allocator, right? So you're right, so no allocator. No standard library. It's actually like this kind of like an interesting observation that you don't need that much from the standard library, really. Like you'll see that it works. But yeah, so the main kind of problem is in languages like C doesn't have any runtime. So you set up a stack, jump to the entry point of a function, and you're running. There is no runtime, right? In C, there is no notion of a memory allocation at the level of the language, right? So it's just a function call which returns a pointer to the heap, right? So in languages like C++, you need to set up some runtime. I did it once. I don't remember how to do it anymore, but like you needed some kind of allocator because it says I want to throw an exception. And if to throw an exception, I want to allocate on a heap. So without the simple allocator, I'm not going to even compile. And maybe it has changed because I'm pretty sure that they worked on how to enable this bare metal C++. And maybe today it's just easy. You just forces compiler not to throw exceptions or something like that. But something similar is happening in Rust. So, and for this specific part of this class, we're going to be using there is this guy, Philip Opperman, who wrote this blog, and you saw it in the past. It's like build your own OS in Rust at a toy OS. And we will be using a mix of his blog posts because he wrote a good text, and I can do the slides about it, but it just doesn't matter. It doesn't make sense to like say the same thing. We'll do a couple of things slightly differently, but to begin with, that's a good start. So let me start. Let me start there. So I'll essentially it's available from this link, and I'm just basically just switching back to. There's a couple of things. So this is my repo, probably basically nearly verbatim taken from Philip, maybe a couple of years ago, maybe like 5 years ago. It has a couple of branches. One is x86, but this is Rust, right? And at this point, like there are multiple ways how to structure your code. The way I do it, like my Rust function is in this librs, and it's called Rust main. And I have you can and I don't know where you are with Rust toolchain. Rust relies on Cargo. That's their like building thing. In my case, I still like illustrate. Philip does everything with Cargo. I think I kind of use a make file, and we'll scroll through this like step by step to make sure that we all understand. But it's essentially a make file is somewhat similar to what x86 is doing. At some point, to build the kernel, I will invoke Cargo, which will build me a Rust thingy. But I also rely on some assembly files because like to have a multi-boot header, I will like put an assembly file in order to set up the page table segmentation, similar to how we did it in our x86 homework assignment in the undergraduate class. So these assembly files will be linked separately, or build and linked separately, or like build and then I will use a custom linker script. So very similar to x86, right? So let's see what's coming. So again, let's switch to his stack of slides. Not this one. And we still have 15 minutes. The idea is, as you say, like what he starts talking about it is how to build a freestanding Rust binary. So essentially a binary which does not rely on the standard library, right? And like that's like, first of all, like typically the expectation is that when you build a program, you will rely on a libc in the same operating system, and the libc will abstract the system call layer of the underlying kernel, kind of like Linux or x86, right? And provide some additional functionalities like malloc and stuff like that. So there will be some memory allocation available. And so here you have, since you're booting on bare metal, you don't have anything, like you don't have system call to ask to print something on the screen. You have to build everything yourself. So roughly speaking, your operating system kernel becomes your libc, right? And so default scenario for most programs is not to run in this environment. So default is to use the standard library. So in case of Rust, you have to essentially disable it explicitly with this no std attribute. And if we switch to my code here, so if we go into this librs, I say line number 1, no std. So essentially I say like this code will not use standard library. That's fine. So that's what Philip is telling you to do, slightly different structure, but he says, okay, sure, let's do this no std attribute. And his main function is just main, and he uses this print line function. And by the way, I also kind of use print line function here. So my goal here is to essentially boot into, that's the main function of my kernel, right? And my first kind of desired goal is to say, look, I want to print hello world from Rust, right? So what's in between? Okay, imagine I compiled it, right? Like we were just talking. So in order to get to this function from the bootloader, what's involved? No, what's involved is the bits of this assembly magic, and it probably makes sense to stop here just to and just go through this code in one go next time, just so it's in our memory. But to give you an overview, like it's very similar to, like, you can do it in multiple ways, but it's very similar to x86, right? So I will have a multi-boot header. Oh, Jesus, it's not this. So my multi-boot header will be this. I say, look, this is essentially a convention. And when the bootloader like Grub or some other sees this header, it says, okay, I see you're a kernel. So I'm going to load you at a specific address and let you run, right? And so we will place this binary header at the very beginning of the kernel binary. My logic to set up like everything, like some first page tables and segmentation will be in a separate assembly file, which is like boot asm. It's just a stock, it's Intel assembly, right? So slightly different from the GCC one, which we used in the undergraduate class. But essentially, we're going to go one by one through this stuff. Like, I will briefly explain what everything means. And like, there is a couple of interesting use cases, like, like, what do you think this function is doing?
Guessing you define print line.
Yeah, so actually, so like, not surprisingly, everything will have to be built by hand. And so in my console module, I took it from Philip, but essentially it's implementation of things which like either send a character on a serial line or put it on the VGA frame buffer. So essentially he implemented a frame buffer and like this write byte interface, which essentially allows you to scroll the strings and everything. And then there is a little bit of a macro magic here. So I just say, look, I will use a macro system, Rust macro system, to define a print and like define this print line thing. And this print line essentially will like use these two methods of the serial line and the VGA screen frame buffer to put something on both at the same time. And that's essentially my implementation of this print line function. And essentially, just to keep it kind of like in context, my idea is that after giving you this overview, I want you, each of you, to build something like this. Here, I kind of like, I face a problem, right? But I mean, I face a small problem because the size class is like 20-something people. In a 200 people class, I face a big problem. Of course, the fact that everyone works, you know, and submits homeworks. Here, I'm not exactly sure how to assign. So, because everything is publicly available. The repo is public, Philip's blog is public, right? But I want you to learn. So I was thinking that I will assign it just saying, okay, guys, that's the end goal. You can like look at the source, but at least read and like put it together in a single folder. Mine is slightly different from Philip's. And we are working on yet another slightly cleaner, maybe build system. But that's essentially the whole works, essentially, just despite the fact that everything is available. And in fact, I don't ask you to like invent a lot of things. I want you to just read through what Philip is writing. We talk through this in our lectures, but I want you to like essentially assemble it and make sure that it runs, loads on QM, you see hello world. That's homework number one. And then we will keep building on top of it, kind of like initializing the memory allocator, as we said, building page tables, building system calls. And I don't know if Philip has it. Maybe he does actually, but that's the goal. So is it okay? Like this assignment? I don't know. Maybe I can solve it. Pretty sure can. I should try actually. I will try, but they reporting. But my goal is like, if I want to learn, just, I mean, I don't care. I'm gonna like run after you and judge that you cooperated for some there. So the expectation is that. So feel free to communicate those, as I said. Okay, that's the plan. That's fine with everyone. As you see, there is some rust, but it's a very, very minor rust. And like essentially Philip in his blog discusses every line of it. And we're gonna go through almost every line of it on Monday, and then I'll try to assign. But keep working on your rust. And I will try to keep working on mine, because I like, if you ask me, they're like, rust is a funky business as well. Let me find you a couple of lines like this. No one can write. Like maybe AI could write, I cannot, but like some people do. But like there are some, like maybe this one, in his blog post, maybe not in this one, but there were like some kind of like counterintuitive type conversions at typecast, which like, I don't know how to like unsafe. I don't know what it means, but I hope you will. Some PL people will definitely. Okay, let me stop here, and then I will see you Monday. We'll continue discussing how this thing boots, and we'll talk a little bit more like how we plan to implement it as a homework, and then homework, we build it, I keep talking about other things. Okay, thank you. See you then Monday.